The equations of motion of Newton, which we've been studying so far, were believed to be right for over 200 years. And the first time that an error was discovered, and correctly discovered, that is, in the laws of Newton was by Einstein in 1905. The equation of Newton, which is a ddt of mv is equal to the force. Newton added the hypothesis that m is a constant, but it's been found that isn't true, that the correct formula is that m is a constant, which I'll call m0, divided by the square root of 1 minus the square of the speed over the speed of light squared. C is the speed of light and is 300,000 kilometers per second. So the whole result is that. That's all. It's the end of the lecture. For those people who only want to learn exactly what they have to learn in order to know something so they can solve problems, this is all there is to the theory of relativity. It just changes Newton's laws by adding this factor in the mass. First of all, let us remark that this mass change is very small under ordinary circumstances. If the velocity is even as high as the velocity of a satellite, say, going around the Earth at 5 miles a second, since c is 186,000 miles a second, v over c is 1 in 20,000, and therefore the correction to the mass is approximately 1 in a billion, which is quite difficult to discover. The easiest way to deal with this subject from a sheer learning point of view is simply say it's been, since we have lots of particles that go over at any arbitrary speed as close as you want to the speed of light, and we've observed that this is true, and that's all there is to it. However, because the effect is so small, it's rather remarkable that it was discovered so early. That is, it was discovered before it was discovered empirically. It's got a very big empirical effect, but it wasn't discovered that way. And it's therefore of great interest to see how such a law with such a delicate modification, at least at the time when it was first discovered, now when the velocities are small, can have been discovered by the combination of experiment and physical reasoning. And this was done by a number of people put together, of which the final result there was Einstein's final discovery. Incidentally, for your interest, there are two Einstein theories of relativity. One is called the special theory, which was made in 1905, and that's what we're going to discuss today. So strictly, this lecture should be called the special theory of relativity. By 1915, he had another theory, an additional theory, called the general theory of relativity. This latter deals with the extension of the ideas of the former theory to the case of the theory of gravitation. That we won't discuss here. Now I'll go on to discuss this theory of relativity. First, I want to state the principle of relativity. One way to state it is the following. The motion of bodies included in a given space are the same among themselves, whether this space is at rest or moves uniformly forwards in a straight line. Don't copy it down, just listen to what it says. If the relation between the two is that since Mo is moving, his center is moved away by a distance v times the time, where v is the velocity, I'm going to call vu, then the relationship between the various coordinates is clear from the diagram, as x prime is x minus ut and so on. Now we discovered that if we take Newton's laws and substitute this transformation of coordinates into them, and then these laws transform to a new set with all primes. In other words, the laws of Newton are the same in form in the moving system as well as in the stationary one, and therefore you can't tell by making mechanical experiments whether the system is moving or not. In fact, Newton first stated the principle of relativity, and the statement which I read to you was a quotation from Newton. So the principle of relativity has been with us a long time. It was used by various people, in particular Huygens, to obtain the rules for the collision of billiard balls, much in the same way as we used it here in discussing the conservation of angular momentum. So what's all the excitement? Excitement is this, that physics does not stand still, that during the intervening years, the phenomena of electricity and magnetism and light were investigated and studied carefully, these culminating in the Maxwell's equations, which describes electricity, magnetism, and light in one uniform system. Now, the thing that's interesting is that the Maxwell equations did not seem to obey the principle of relativity. That is to say, if I took Maxwell's equations and made that substitution in them, their form did not remain the same. Therefore, there would be phenomena, electrical and optical phenomena, which would be different in a moving ship than one standing still. And thus, you could use these optical phenomena to determine the speed of the ship. In particular, for example, you could determine the speed of the Earth, absolute speed of the Earth, by making the suitable optical measurements or electrical measurements. Now, let me give one illustration of a measurement to give you a quick idea of what I would talk about. One of the consequences of the Maxwell's equations is that if there's a disturbance, then light is generated, or electromagnetic waves, depending on the frequency, of course, is generated, and that these waves go out in all directions equally and at the same speed, which is 186,000 miles a second, or c. So if a light is going along here, it goes at the speed c, and it also is a consequence of the same equations that if the disturbing thing is moving, the light comes out at the same speed. It's like sound. It doesn't make any difference whether the source is moving. The sound just goes at the same speed. So the speed is independent of the source movement. Therefore, we have an interesting problem. So we have a car here, and we let a light source go out. Well, we say we're riding in this car, and somebody sends light past it going at the speed c, and the car is going at the speed v. Then, of course, according to those things here, if you differentiate, you get that the speed measured, the derivative of x prime, differs from the other speed by the speed u. The car's going at the speed u. Therefore, the apparent speed of the light shouldn't be 186,000, but should be that less the speed of the car. For instance, if the car's going 100,000 miles a second, and the light's going 186,000 miles a second, then apparently the light going in past the car should go at 86,000 miles a second. And therefore, by measuring the speed of light in the car, because it doesn't make any difference whether the light was sent from something outside or something inside, make a little hole, let it go through, and measure the light, it should be a different velocity. And thus one could determine the speed of the car by measuring the behavior of light. Well, a number of experiments were performed with this general idea in mind to determine the velocity of the Earth, and they all failed. They all gave no velocity. We'll discuss one of these experiments in detail in order to show what was done exactly and what was the matter. Something was the matter, of course. Something was wrong with the equations of physics. Now, the first thing to think of course, is that the new equations, the Maxwell equations of electrodynamics, since they're mostly new and they were only 20 years old, were obviously the ones that were wrong. Now, what Einstein's, or actually it was Poincaré's idea originally, was to propose this, that all the physical laws should be of such a kind that this is the right transformation to make so that they remain unchanged. In other words, we will change the laws not of electrodynamics, but the laws of mechanics. We'll change Newton's laws so that they won't remain unchanged anymore under this. But they will remain unchanged under this. And there's that set of reasoning which proposes what kind of modification Newton's laws has to undergo. We have to rewrite them in such a way that if we make this transformation of coordinates instead of this one, they will remain the same. And then it's a matter of, with that clue, it's a matter of fishing around with the equation to try to find out how to change it so that if you make this transformation, it'll remain the same in form. And it turns out that the requirement is only that the formula looks exactly the same, except that the mass must go like this. Under those circumstances, Newton's laws and electrodynamics will all go together. And if we believe that when we could compare Mo's measurements with Joe's measurements, we should have used this relationship instead of the other one, then we'll never be able to detect any phenomena, because the form of the equation will be the same. Any phenomena to determine that the thing is moving. This is called the Lorentz transformation, and just for the sake of discussion, this is called a Galilean transformation. I don't know how to spell it. Galilean transformation. It is also necessary, of course, not to just leave the thing here. It's all right to leave it here, but it's certainly interesting to try to discuss what it means that you have a new transformation between the coordinates and time rather than the old one, because this one seems to be self-evident and this one looks peculiar. And so the first thing to try to find out is it possible, legally, logically, and experimentally possible, that this is the correct transformation and not that? So that in addition to studying the laws of mechanics, we also have to analyze, Einstein also had to analyze the ideas of space and time required to understand this transformation. We have to discuss these ideas now, and of course to discuss these results from mechanics, but I may say, to justify all the effort that we're going to make, that all the results are in agreement with experiments, so that it's worth doing. In order to explain more clearly how people had intended to make this these effects, to measure the speed of the Earth through the ether, I'll take one experiment, the most famous, in fact, called the Michelson-Morley experiment, made in 1887. It was 18 years before it was finally straightened out. And this was the following experiment. You take a L-shaped thing, make the two lengths equal. Actually, well, it's a technical point, but you can essentially make them equal, or you can make subtractions so you don't have to worry about that. So that this length here is L this way, and this length here is L also. And then the idea is this, that it's possible to take a beam of light and split it, so part of it goes down and goes back here, and the other part goes up and comes down, and to compare the times at which the light arrived with extreme precision, because as you know, light is a wave, and by making an interference measurement here, if there's a slight difference in time at which they arrive, there's a difference in phase, and certain interference fringes are shifted. So what we're going to try to do is to demonstrate first that we would expect a difference in time for going down and back and for going up and down if this whole thing is moving. Of course, if it's not moving, there would be no difference in time. But if it's moving, there should be a difference in time. Let's see why there should be a difference in time. First, let's analyze the beam which goes down to the end and back. Let's say it's going down, but the whole equipment is moving this way with a velocity u. Under those circumstances, the picture looks something like this. If this is the original position of the bar, and the light starts from here and goes down for a time t1 to hit the end, at the end of the time t1, of course, the bar has moved, so this distance is v times t1, the time to go down to the end, while the light traveling at the speed c travels all the way to the end in the same time. See that as it moves down, the rod moves, so it has to go a little further to get to the end. And therefore, since the length of the rod is L, we have that CT1 equal VT1 plus L, or that T1 is the length divided by C minus V. So this distance is CT3, and this distance is the length of the rod L. So we have a triangle which tells us that C squared, T3 squared, and so on. No? And therefore, it comes out that T3 is equal to L over the square root of C squared minus U squared. You see, if you square this, it says that. It says that L squared is C squared T3 squared minus U squared T3 squared. But it must return also, so that the total time down and back at the return time is the same. So the total time the other way, 2T3, is equal to 2L over C. I'm just rearranging the formula a little bit. 1 minus U squared over C squared. And this one I want to rearrange also to the form 2L over C divided by 1 over U squared minus over C squared. Thus, now they're both made. The reason I do it this way is that obviously 2L over C is the time it would take to go if the thing was standing still, and these are very small modifications. But look, the modifications are not the same, and therefore there's a difference in the time it takes to go up and down as it goes to go along if the whole thing is moving, and therefore all we have to do is measure that difference. There's a little technical trouble. How do you know you got the lengths exactly right? Well, you just turn the apparatus this way, this way, this way, and so on, and measure whether there's any shift in the fringes. In other words, just a technical point, but if you're worried about the fact that you can't get the rods exactly the same, if the time, for instance, to go down and back this way is longer than the other one, then when you turn it this way, it will become the shorter one, and the fringes will shift as you rotate this apparatus in a plane. So that's just a technical experimental point. Now, the fact of the experience the experiment is that it doesn't happen. That is, that there's no effect of turning the apparatus. Therefore, something the matter with this analysis. And after mumbling around a while, Lorentz pointed out that it would all be straightened out if you will assume something, which is that when a rod moves in the direction of motion, it shrinks. Let's suppose, he said, that although L0 be the actual lengths of the real thing when standing still, that when they move, this distance is L0 all right, but that the other one is foreshortened and becomes a thing which we'll call L parallel, let's say. And if we suppose then, if we calculate this again, then that this should have been L parallel, and this should have been the perpendicular, which we'll take to be L0. Then if we can say that L parallel is shorter than the way it would have been at right angles, L0, if we suppose this, then of course this one, the square root will go into this and it will make them equal. So he said that a way of understanding that the Michelson-Morley experiment doesn't give any effect at all is that the rod shrinks along its length. Well, there were many other experiments beside the Michelson-Morley experiment, and for each experiment, somebody or other concocted some kind of a gimmick like this that might screw up the experiment. Until there was talk of a conspiracy, that every time there's a phenomenon, there's another phenomenon which undoes it. And ultimately, of course, as Poincaré pointed out, a complete conspiracy is a law of nature. So he proposed that that's a law, that there'll always be something which will do this. And that was the principle of relativity then, will be maintained. We'll propose as an idea that it's impossible and no experiment will ever work by which you could tell your absolute velocity, and therefore that all the pieces of analyses and all the gimmicks that have to be invented are, in a certain sense, real. Now, if we do suppose that this, now that's the end of the idea, and now I would like to say a few other things. First of all, it turns out, just a qualitative description of what happens. Not only must lengths shrink, but also the times must be different. You see, the time t3 that I calculate for going up and down is not the same as the time that the man is riding in the spaceship calculates for going up and down, because that's this, and they differ by that. So that means that in the spaceship, times appear to things take longer to happen than they seem, when I look at the spaceship, than they do to the man inside. In other words, when I look at the man riding in the spaceship and lighting a cigar, he does it very slowly and puffs and so on, while for his point of view, it's going along at the regular rate. So not only must lengths shift, but the clocks must apparently slow up. And it turns out, by looking at this, that the clocks must slow up by the same factor, 1 minus u squared over c squared. This particular fact, that time slows, has been directly measured experimentally very recently. But, well, we'll come back to that, excuse me. When they're moving, then they're moving very close to the speed of light. The time in their point of view is this, but from my point of view is much longer. So they last longer and they get down here. And the length of time that it takes them to disintegrate on the average for moving meson has been measured quite accurately for different velocities. And of course, the length of time they live is different for different velocities in the correct proportion as the square root. We don't know exactly what makes the mu meson disintegrate or what the machinery is, but it satisfies the principle of relativity. That's the utility of the principle of relativity. It permits us to make predictions even about things that we don't know any otherwise very much about. For example, before we have any idea what makes it disintegrate at all, we can still predict that when this thing is moving 9/10 of the speed of light, the apparent length of time that it lasts is 1 over the square root of 1 minus 9/10 and so on, into 2.2 times 10 to the minus 6 seconds. And it works. That's the good part of it. Now, we would like to understand the relationship between these coordinates, between this system and this system, and I'd like to show you how we can understand it. We've already noted that the rods shrink. How can I say that, prove the rods shrink? Well, we just pointed out the times must be equal. These distances cannot change. I gave the argument why, that this still is L0, so that in order for this not to work, this rod must appear shorter by that square root. That means that, from my point of view, the man who's making his measurements in here is using a foreshortened ruler. Therefore, if he measures x prime units with his foreshortened ruler, the actual distance that I would say it is not x prime units, as he thinks it is, he lays the ruler down 79 times, the distance is not 79 meters from my point of view, but it's 79 meters foreshortened. And this, when added to the v to the ut, must equal the x that I measure. And that is the reason why x prime is x minus ut over the square root of 1 minus u squared over c squared. In an analogous way, because of the difference in time scales, that's the reason for the square root here. The most interesting term of them all is this term in here, because that's quite new and unexpected. And what does that mean? If we look at the equation carefully, it means this. 2 points which I consider at the same time will not appear to be the same time for the other man if they differ in the position along the horizontal. If I say two things happen at the same time and they're far apart, and the question is whether the other guy agrees with me depends on whether he's moving or not. Let's see about that. You see, from my point of view, these two times are unequal. They differ. But from his point of view, the time to go down, the time to come back are equal. So there must be some reason, something, which allows us to contemplate the possibility that the times, when I say that two times are equal from one point of view, they're not equal from another point of view. And it depends upon the fact that it's moved down a distance in x. To make a little more clear this important point, which is called failure of simultaneity at a distance, we can take the following experiment. I suppose that there's a man in a ship, which is again idealized as a rod, who is interested in making sure that the two clocks which he has placed at the ends of the spaceship are in synchronism.